we're moving from surfaces to curves. And our next speaker is Hasan Pourmahmood Aghababa, who is going to speak about orientation preserving vectorized distance between curves.
Yes,
So
thank you. Thank you. Okay, hi everyone, and welcome to my talk. I'm going to talk about an orientation preserving vectorized distance between curves, which is my joint work with my advisor Jeff Phillips at University of Utah. Okay. Consider two trajectories with m waypoints. By a trajectory, I mean a piecewise linear curve, or let's say polygons. We want to know how can we measure their distance. Okay, there are some popular distances like Hausdorff distance, but Hausdorff distance does not pay attention to the direction of the curves. By orientation preserving property, I mean if we have two curves that are geometrically the same, but let's say with different directions, then the distance should assign a positive value for these two curves. Okay. This Hausdorff distance does not have this property, and the complexity of calculation of the distance is big O of m. The next three popular distances that I'm going to talk about are dynamic time wrapping, Fréchet distance, and discrete Fréchet distance. All three metrics do preserve the orientation of the curve, but their complexity is O of m squared. Okay, so they are a bit slow when m is large. So when they are problematic or inefficient, in fact, when m is large, these distances are slow. And so, for example, KNN, I mean K nearest neighborhood algorithm, and almost all clustering algorithms with these distances are expensive. Okay. And more importantly, these metrics does not allow us to take the advantage of other machine learning algorithms because, you know, they need a vector type input mostly. Okay, so we're interested in a distance that address the above mentioned problems and be as fast as calculating Euclidean distance in a Euclidean space. Okay, so formally by a curve, we mean a continuous mapping, continuous image, the image of a continuous mapping from the unit interval 0, 1 to R2. Towards this goal, Jeff Phillips and Ping-Fan in 2019 introduced a landmark-based distance. And I'm going to talk briefly about this distance because our work is a generalization of this work. So for a curve gamma and a landmark point in R2, they define the VQ mean this function by just taking the distance of the point Q from gamma. Gamma is a compact subset of R2, so Q can attain the mean point. And so this function is, by taking the minimum, is well defined. As you see, if we have two curves that, they are the same but with different directions, this VQ function will assign the same value for both of them. So if we want to use this function to make a distance, it will not preserve the orientation of the curve. Okay. Now they use a vectorization technique. In fact, they choose just some points as landmarks in R2, and then have a function, I can say a feature mapping, which is from curves to Rn by just vectorization of the VQ function. This is a pictorial sense of view that shows when we go further away from the curve, the VQ function value increases. Now the mean distance is defined in this way. In fact, they embed the curves into a Euclidean distance and then take the usual Euclidean distance between two curves, between two embedded vectors. And just they normalize it because of some nice properties. Okay. As you see, the complexity here is big O of the size of Q, and they have proved that if Q is dense enough, ignoring the direction of the curve, this distance should be a metric on the space of curves. And as I said, it's not orientation preserving, and we're interested in to know how we can encode the orientation preserving property into this distance. My contribution starts from here. We have some small definitions. By a simple curve, we mean a non-self-crossing, possibly closed curve. In fact, the fundamental group should be trivial. And by gamma, capital gamma, we show the class of simple curves that are almost everywhere differentiable. So the tangent line exists, and so the normal vector can be defined. And by n sub p, we denote the unique normal vector at p on the curve gamma, for example. Considering the direction of the curve, we have a unique normal. If we don't consider, we have two normals, but considering the direction of the curve according to the right-hand rule, we can have only one, which is well defined. Now we define the sign dist function in contrast to the mean dist function, which is parameterized by a number, real positive number, sigma, and a landmark, Q. It is defined by 1 over sigma times the inner product between the normal vector at P on gamma and the vector from P to Q. P is the arc mean of the point that gives the minimum distance from Q on gamma. And then we multiply with the Gaussian weight parameterized by sigma value. This is the definition for the case that P is not an endpoint of gamma. And as you see, if we have two curves that they are geometrically the same, but with different directions, our VQ sigma function will assign positive or negative values. So it means it is orientation preserving as a function. And for endpoints, if P is an endpoint, we have roughly similar formula, but I'm not gonna go through the details of this, that why we define in this way. Just to mention that this helps us to verify the definiteness properties of the metric. This is a pictorial sense of VQ sigma function, which is encoded by positive negative values for a curve with sidedness. So if a landmark is above the curve, then our VQ sigma function will assign a positive value, and on the other side will assign a negative value. Now, similar to the min-dis vectorization, we can vectorize our VQ function to get feature mapping from the set of simple curves to Rn. And this is one of the biggest advantages of our work, because it makes possible to use machine learning algorithms, because we're embedding everything into a Euclidean distance. And so almost all algorithms are applicable. And we will drop the sigma notation for convenience. Now the orientation preserving distance we introduce is the Euclidean distance between the two embedded curves in the Euclidean space. So first of all, we take two curves and then we embed in a Euclidean distance with the dimension of the Euclidean distance is the size of Q. And then we're taking the usual Euclidean distance between them and then we normalize. So it's just normalized Euclidean distance between two vectors. The complexity is big O of the size of Q, and because we're using VQ sigma function, it's obviously considering the orientation of the curve. So it will assign a positive value for two curves that are geometrically the same, but with different directions. And for being a metric, we need to have Q to be dense enough. But in practice, we've observed that 20 landmarks are enough to do data analysis tasks for trajectories. We have some theorems that first of them is landmark stability, which says under some mild conditions on two landmarks Q and Q prime, we have the following inequality. This is a nice inequality because it shows the continuity of our VQ function, in fact VQ sigma function, which we've dropped the sigma notation here. So it shows the continuity in terms of perturbations of the landmarks. And the second one is about curve stability. Again, under some conditions on landmarks, we can show that our distance is less than or equal to the constant times the Fréchet distance between two curves. Since the Fréchet distance is continuous in terms of perturbations of curves, so our distance also is let's say continuous in terms of the perturbations of the curves. Okay. In contrast, the DQ min-dist function, which I introduced previously, it relates to the Hausdorff distance, and we have a similar inequality for DQ min-dist with Hausdorff distance. So again, it shows the continuity of the DQ min-dist function. These are some of the theorems and results which we have sampled for giving this talk. And my last slide is about experiments. Using these two feature maps, VQ and VQ min-dist, we've done some experiments, which I'm presenting a small sample of them here. In fact, this is a binary classification test. For example, for car bus dataset, we want to classify car trajectories from bus trajectories using our featurization and the previous min-dist featurization. And the characters dataset is, in characters dataset, we're trying to classify two letters, for example, A and B from each other, which are drawn on a tablet. Both of these data sets are in machine learning repository. And the third one is pigeons dataset, which is the track of the flights of some pigeons from point A, for example, to point B. We took all the trajectories in pigeons dataset and reversed half of the tracks and trajectories direction. And we want to see if we can detect the direction of the curve. It means a pigeon goes from A to B or B to A. Okay, and as you see, we've got the best errors and test errors with RVQ sigma featurization. On most data sets, we saw that they perform similarly, but when the direction of the curves is essential, like this in this pigeons data set, our featurization can get 0 test errors, so the accuracy is about 100%, but the VQ mean this function that does not respect the orientation of the curves cannot do better than chance. And these are the average test errors of 1,000 trials. And as you see, we've tried several classifiers like SVM, decision tree, and random forest. And these are some references. This work is accepted to MSML conference and will be after some months. And that's it. Thank you.
Thank you. And we do have the time for a few short questions. I see Aras has raised his hand.
Hello. Okay, can you hear me now?
Yes.
Yes.
I have two questions actually. One, can you give a more concrete example of the trajectory problem? Like maybe for the pigeons, like what would the trajectory be and what would the landmarks be?
Oh, okay. For pigeons, we have pigeons are flying from, for example, one city to another city, from city A to city B, and we have them their flight path. Okay, so and we've changed the half of the path's directions. So half of the curves are from A to B, and half of them are from B to A. And we're trying to detect if a pigeon goes from A to B or B to A. And landmarks are randomly chosen. 20 landmarks are randomly chosen around the curves.
Just randomly chosen?
Yes, just randomly.
Interesting.
Yeah.
Cool.
And we're working on optimization problem regarding this to optimize the place of landmarks to get better results, better accuracies.
I see. Cool. And then you classify it. Cool.
Yeah.
Okay. And second question, can you go? What's a graph with the red and blue distance map from the curve, and I just noticed that the distance kind of goes to 0 once it gets really far from the curve. And why is that the case here?
Exactly. Here, the value is 0. The value of our VQ sigma is 0 because of this property. The NP dot product between Q minus P and NP for this, because of this notation here, it becomes 0. In fact, if you consider NP here, the normal vector, it is orthogonal to this vector. So if the point is here, the inner product is 0.
And what about in the area where it's like directly above the curve and then you go really far out? Like my intuition says that if you go far from the curve, then it should be more positive, but it seems to tend to 0.
That's yes, that's for the mean this function. This is because of this Gaussian weight. After the maximum value you get is here. If you go further away, you will get 0 values.
Interesting. And that is good. It's just...
Thank you. That's a localized distance.
I see. Huh. Interesting. Okay. Thank
Any
you.
other quick question? I do have one.
Okay.
In practice, how do you choose the width of your Gaussian, the sigma?
We just first we chose by the distance between taking a look at 2 data sets, which we're trying to, let's say, classify. For example, car and bus data sets, and decided to have something roughly half of the distance between their mean value, the average value. But actually, we can optimize this sigma by taking the gradient and the gradient of this distance with respect to sigma, and then doing a gradient descent based method for optimization and getting the better sigma values. So it's possible to get better sigmas, but in practice, we use only, as I said, the half distance between 2 set of curves that we're trying to classify.
And my final question is it guaranteed to be a metric?
Yes, as I said here, we need Q to be dense. If Q is dense enough, for example, consider a bounded region and all the curves are here. If Q is dense enough in that place, in that region, then dq sigma should be a metric, yes. But on the set of set gamma, which includes only simple curves.
Okay. So thank you again, Hasan, for this interesting talk on how to maintain orientation when comparing curves. Our last speaker in this short talk is moving back to surfaces.